induction furnace has long replaced the traditional cupola furnace in the foundry sector. However, with growing competition and rising energy cost, operating an induction furnace has become the prime area of concern. An induction furnace consists of a non-conductive crucible surrounded by a coil of copper wire. The power source supplies powerful alternating current that flows through the wire. The coil creates a rapidly reversing magnetic field that penetrates the metal. The magnetic field induces eddy currents, which heat the bulk metal by Joule heating. The intensity of power supply drives the efficiency of the furnace. The power source panel converts the AC input into DC output. The output is then fed into an inverter through the DC choke. This is then further inverted to the AC output of 0.5 kHz to 50 kHz as per requirement. The power received is then fed to a tank circuit, which is a combination of an inductor and a capacitor. Conventionally, silicon-controlled rectifier-based power circuits are used, which have some inherent disadvantages such as low response time, low power factor, creation of harmonics, inability to be used at higher frequencies, leading to increased melting cycle time. An insulated gate bipolar transistor, popularly known as Igbt-based power circuit, is an energy-efficient alternative to the conventional system. It's a 3-terminal semiconductor device with huge bipolar current carrying capability. Igbt is a functional integration of power MOSFET and BJT devices in the model of performing. An Igbt possesses high input impedance like a MOSFET and has a low on-state power loss as a BJT. The pulse width modulation is used to reduce harmonics and improve efficiency of the system. A 12-pulse Igbt-based converter maintains a power factor close to unity, increasing power intensity, reducing cycle time for melting. The system saves a significant amount of energy. Benefits of Igbt-based induction furnace include improvement in power factor up to 0.992, reduces harmonics as per CERC-CEA standards, that is, less than 8%, can operate at higher frequencies, less melting cycle time, higher furnace efficiency, reduction in energy consumption. To understand the cost benefit, let us consider a unit of 2000 tons of annual production. Replacement of conventional SCR-based induction furnace with Igbt-based induction furnace, along with the adoption of best operating practices, will lead to a saving of 8 to 10% of specific energy consumption. The investment required for a 500 kg Igbt-based induction furnace is approximately 30 lakh rupees, which can be recovered within a period of 4 years. Added benefit in terms of life of equipment and higher power factor can be achieved. The annual energy saving from the intervention is approximately 12 tons of oil equivalent of energy, leading to a monetary saving of 8,45,000 rupees per year and around 115 tons of carbon dioxide emissions per year. An automatic demand controller will help in optimizing the performance of the induction furnace. Proper scrap segregation and processing helps in optimizing the energy consumption. A 24-pulse system can further improve the power intensity. Many indigenous technology providers are available across clusters for the technology. Although the Foundry cluster has been undergoing a technological shift from coke-based cupola furnaces to electrically operated induction furnaces, immense scope exists for further technology modernization and energy savings in process technologies such as Igbt-based induction furnaces. If implemented in 100 units, the technology can save 1200 tons of oil equivalent of energy and 11,500 tons of carbon dioxide emissions annually.